Hello everyone, welcome back. Today we are going to dive into CMake and build a solid understanding of how it works behind the scene to configure, compile, and build your C++ project. This tutorial is for anyone who wants to use CMake, but it is part of my GDExtension tutorial video series. So even if you don't use GDExtension, this video can help you. So what is CMake? CMake doesn't directly turn your .cpp file into programs. Instead, it generates the file your compiler actually needs, like Makefile, NinjaFile, or Visual Studio Project file on Windows. So think of CMake as a meta build system, a generator that makes other build systems. This means you can write one CMake configuration and build your project on any platform without rewriting everything. I already told you how to install CMake in previous video, and if you install that, no matter on what operating system you are, everything should work same. Here I have a Manjaro Linux, and in this folder I intend to write a basic CMake file. Here I just create a text file and I name it CMakeLists.txt. Pay attention, your file should have this exact name. Now every CMake project starts with these two lines. First is CMake minimum required, which inside that we have version keyword and then the actual version number. This ensures you are using at least this version, because newer CMake feature may not exist in older version. Second is project, your project name, language CXX, which gives your project a name and specify the language C++ in this case. By the way, specifying the project language is optional. Well, now we have created our first CMake. Let's see how we can run it. Usually we run CMake in directory called build, which contain all the cached variable, compile object, and other generated files. So inside the build folder, I run CMake ... which means I'm running CMake using these configuration files from the parent directory. You can see that a make file has been generated for us. However, if I run make, nothing happened because we haven't defined any build target yet. What I like about CMake is that it separates all the configuration and build file inside the build folder. You can even have multiple build folders with different configurations. Now before doing anything else, let's open this folder in VS Code. Also make sure you have the CMake tool extension installed. CMake uses its own scripting language, which can feel a bit strange. It is not quite like any other programming language. It was first created in the early 2000s to simplify building large C++ projects across different platforms. But the good news, it is easy to learn. In CMake, the message function is used to print text to the console. The first part specifies the message type, like status or warning, and the second part is the actual text you want to display. In CMake documentation website, you can find all different possible message types. So here, if I run CMake again in build folder, you can see the message hello CMake. Okay, now let's talk about variable in CMake. In CMake, you can create a variable using the set function. The first argument is the variable name and the second is its value. To access the value of the variable, you wrap its name in parentheses and add a $sign in front of it, like this. So now if I run CMake, you can see hello Alice. The important thing about variable in CMake is that they are all stored as strings. For example, I can remove the quotation marks around Alice and everything still works the same. Here I have created another variable called my age with a value of 35. Even though it looks like a number, it is actually stored as a string. Of course, you can still perform math operation or comparison on it. CMake automatically converts the string to a number when needed, depending on the context. So I can also add my age in hello world message. CMake also defines many special variables automatically when you run it. For example, CMake source directory refers to the source directory which CMake runs. And CMake binary directory points to the build directory. There are many other built-in variables as well. Now in CMake, sometimes we don't just need a single string variable, we need a list of values. You can create a list by writing multiple items separated by semicolon. For example, here I create a list of fruits, each one is separated by a semicolon, and then I print them. Okay, this is a printed list. There is another way to create a list without using semicolon. You can simply remove the quotation marks and separate each item with a space. But be careful, if you keep the quotation marks and use spaces, it won't be a list anymore, it just be a long string of text with a space in it. Now when you have a list of items, you can perform various operations on them. Most of these are done using the list function. The first argument of the list function is the operation you want to perform. In this case, I want to get one item from my list. So I use the get operation, then you specify which list to operate on, followed by the index of the item you want. Here I'm getting the first item, which has an index of 0. Finally, you specify where to store the result. In this example, I save it to a variable called first fruit. So now if I print the first fruit, you can see apple name printed here. Now there are more operations you can do on a list. In CMake website, you can find them all. Now for a practice, let me append some element into my list. So I append some duplicate elements into my list and remove duplicate from the list. I think you get the idea how this works. Now there are many other functions in CMake that work similarly to list. One of the most important one is the file function. With it, you can perform various operations on file. You can read or write them, rename them, get their size, and even download or upload files. Later, I will use file glob and glob recurse, which retrieve a list of files in the directory. The glob recurse version does this recursively, and you can also filter files using patterns. As an example, I can use this function like this. The first argument specifies the operation, in this case glob recurse. Next I provide output variable followed by the directory path and patterns. Here this will get all .cpp file inside the directories and its subdirectories. Okay, now let's talk about if statement in CMake. To create an if statement, you start with the if keyword followed by parentheses that contain your condition. And don't forget, every if statement must be closed with int if at the end. You can put else if like this and else like this. Now let's check if banana exists in the fruit list. First, I type the term I want to check, then I use inList keyword, and finally I specify the list. If I want to negate that condition, I can add a not keyword. In CMake, there are many keywords for comparing or checking condition between the left and right terms. For example, to compare number, you can use the equal keyword. To compare a string, you can use str equal keyword. Another useful keyword is exist. We check if a file or directory exists on your system. For instance, I can check if the build directory exists like this. Here CMake source directory refers to the folder where when your main CMakeLists.txt file is located, and build is a subdirectory inside it. Some of you might ask if it is okay to use / for subdirectories. And the answer is yes. CMake automatically converts the path internally to / on Windows system. Another useful keyword is directory, which return true if the path is a directory or not. There are a lot of these keywords which you can use. I put some of the most important one on the screen. You can pause to check. Also, you can check CMake documentation. Okay, now let's talk about loops. In CMake, foreach is a loop that lets you repeat command multiple times, just like in most programming language. You can use it to go through all elements in the list or loop over a sequence of numbers. So as an example, let's loop through this fruit list. First, I use the foreach keyword, and inside the parentheses, I specify the name of the variable that represents each item in the loop. In the middle, I use the inList keyword to tell the CMake that we are looping through a list. And finally, I specify the list itself. Inside the loop, I can print each item names, and when I run CMake, you can see that all the items in the list are printed. If you want to specify your item name in place, you use in item keyword and then specify your item after that. Now let's see how we can loop through a range of number. For that, you can use the range keyword, followed by the upper limit of the range. In this example, you can see it's printed number from 0 up to 3. But pay attention, it's include 3 as well. If you have coded in Python before, you know that the Python range function does not include the upper limit. You can also specify the lower limit of the range. For example, here I set the lower limit to 1 and you can see its print number from 1 up to 3. It is also possible to specify a step value in the loop. For example, if I set the step to be 2, CMake will loop through this range of the number by increasing the value by 2 each time. In CMake loop, we have also continue and break. As an example, here I have a set of number in a list. And in the loop, I just continue if number is equal to 4. Also, I will break if the number is greater than 5. If I run this CMake, you can see the result. So that was about loop. Now let's talk about how we can create functions in CMake. To create a function in CMake, you start with the function keyword and end it with the end function. The first argument inside the parentheses is the function name. For example, here I have created a function called print message. After that, anything you put inside the function definition will be treated as a function argument. For example, here text is an argument. Now let's just print the text. So here to use this function, I just use the function name and passed my argument. Okay, as you can see, it is working. In CMake, functions have their own scope. What does this mean? Here I declare a variable called myVar in the global scope. Then inside my function, I change its value to inside and I print that. When I call this function and print my var, you can see that the variable change inside the function but not outside. This happened because changes inside the function are local by default. If you want to change the variable globally, you can add the parent scope keyword at the end of the set command. This updates the variable in the global scope while keeping the local value unchanged. You can also set it locally again inside the function like this. Now, as you can see, my var is changed in both scope. Okay, now let's see how we can create a function that returns something. For example, I want to create a function that generates a list. The function takes 3 arguments: prefix, which is added to each item in the list, count, which is the number of the items, and outvar, which will store the returned list. Inside the function, I first create an empty temporary list, then I use a foreach loop to iterate from 0 up to the count. For each iteration of the for loop, I append a new item to the temporary list in the format of prefix underscore index number. Finally, I set the value of outvar to this temporary list. The key point is that you need to reference outvar using a $sign and curly braces. So we get what user passed to this function. Then we use the parent scope option to update the variable in the global scope. Now I call this function to generate a list of 5 items and I print that. You can see all items are printed here. In CMake, beside function, we also have macros. A macro is very similar to the function, but it behaves differently when it comes to variables. All variables inside a macro are in the global scope by default. For example, here I create myvar and I change its value inside macro. When I call this macro, you can see that it changed the value of the variable globally. Functions are generally considered safer because they don't modify global variables unless you explicitly use parent scope. Okay, up to this point, we know some basic stuff about CMake scripting language, but our CMake don't do anything yet. So now let's define some target to build. In CMake, a target is anything that you can build, an executable, a library, or even something custom. So let's compile something with CMake. I've just created a source directory and inside that a file called main.cpp. In this file, I've added a simple C++ hello world program. Now in my CMake file, I create a variable called mysrc and add main cpp to it. Note that CMake current source directory give us the current path of the CMake file. After that, I use add executable to create an executable named hello, and I add my source file to it. Now, if I run CMake and then make again, you can see we have our hello program built successfully. What we just did was create a target for CMake to build. Each CMake project can have one or more targets, and in this case, our CMake file currently has only one target named hello. Now imagine we have an include folder. I have created this folder and added a header-only file that contains code for a vector2 class. Now I want to use this vector2 header file in my main program. Here I include the header file, but as you can see, it is not recognized because neither CMake nor VS Code know about this file location yet. For now, I'll manually add the include directory path in VS Code so I can recognize the header file in editor. But if I try to compile that with CMake and make, you can see it does not recognize the include directory path. Now the way you can add an include directory in CMake is with include directories function. And as you can see, this time my code compiled without problem. Now if you add include directory this way, every compiled target will use that include directory. For example, here if I add a target B here, even target B will include that. Sometimes that is fine, but other times we might not want that behavior. To add an include directory only for a specific target, in this case our hello program, we can use target include directories function. The first argument is the name of the target, which is hello. The second argument defines the scope, which can be private, public, or interface. I'll explain this in more detail later in this video. And finally, the third argument is the include directory itself. As you can see, our code is still compiled perfectly fine. In CMake, we also have several other functions related to the build target. You can see some of them here. There is also another useful function which you can use to set some of the properties of the build target. In set target property function, first I declare the target name and properties keyword. And here I can change some properties of the build target. As an example, I can change the build path of the executable by overriding runtime output directory property. Here I set it to the bin directory inside the build folder. I also set my C++ standard to C++ 17. Note that if you want to change C++ standard for the entire project, you can override CMake CXX standard value. For example, here I change the project's C++ standard to C++ 14. There are a bunch of other target properties which you can override too. You can read more about them in CMake documentation website. Now if I recompile, you can see my hello program will be added inside bin folder. Okay, up to this point, our CMake file only contains a few lines of code. But for a real large project, a CMake setup can be much bigger than this. You might also want to compile your project for different platforms, each with its own specific function. Obviously, we don't want to put all the CMake code for a big project into a single file. That is where the include function comes in. Here I create a directory called CMake, and inside it I create a file called extra.cmake. In this file, I'll add two lines of the CMake code. The first line print a message, and the second define a variable. Then I just include this file in my main CMake using include function. When I include this, CMake open this file and execute everything inside that. You can see that the inside extra.cmake is printed and the variable will also be set. You can use this approach to organize your code, put the function definition in separate file, or split different parts of your project. There is another way to organize your project into multiple sections using CMake subdirectories. With add subdirectory function, you can add a subfolder that has its own CMakeLists.txt file and even its own targets. You can also use CMake subdirectories to include another CMake project, such as external C++ library, directly into your project. So in this project, imagine I have a section called app and I want another CMake file to handle that. Inside the app folder, I have two directories, one for the source file and one for the header file. In the header directory, I create a file called add.h where I declare the add function. Then in the source directory, I create add.cpp and inside it, I define the function body. Now let's define a CMake file inside this folder to create a static library from this file. I start by setting the minimum required CMake version and defining the project name. Then I use the add library function to create a library called myapp, and I add the source file from the source directory. One important thing to note is that the CMake source directory refers to the top level CMake location. Since we are working inside the subdirectory, we should use CMake current source directory instead. This gives the path of the current directory, where this specific CMake file is located. Another important thing about the library is that we should add app include path. For that, I use the target include directory function. Here my target is my app, and this is where the target scope becomes important. Basically, we are creating this static library so it can be used and linked in our main CMake file that built the executable. Now for the include path, we have three scope options: public, private, and interface. If I use public, it means that when this static library is built, this include path will be used for building this static library. And also any target that link against this library will automatically get the same include path. For example, if the main executable links to my app, it will also see the header from the app include folder. If I use private, the include directory is used only when building this library. This is useful when your library has internal header that you don't want to expose to other targets. And finally, if I use interface, the static library itself doesn't use the include path when being built, but any target that links against it will use this include path. This is often used when your library doesn't have its own source code, but provide a header interface for other. For example, a header-only library or a wrapper around an external header. And finally, I add my include path. In the add library function, I didn't specify whether a library should be static or shared. By default, CMake usually creates a static library. However, since this default behavior can be changed in some setups, it is a good idea to explicitly mention the static keyword to make sure it's always built as a static library. Now in my main CMake file, I use the add subdirectory function and pass the app directory path. This automatically loads the CMake file inside that subdirectory. At this point, my app library is recognized by CMake, so I can use that. Here I call target links library, where the target is my hello program, and I link it with the private scope. This basically means that any target depending on the hello won't automatically link to my app. In this case, it doesn't matter since no other target used this executable. Also, our library include path is already applied here because we defined it with the public scope LReal. In my main.cpp, I use this library just to make sure everything works correctly. Then I rerun CMake and recompile the project. You can see that my hello program runs successfully. And if I look inside the build directory, there is now an app folder, and inside it, you can see the static library we created earlier. Okay, now the story with the CMake isn't finished yet. In the next video, as I create my GDExtension project, I'll show you some more useful tweaks and tips for working with CMake. So until the next video, have a great time and bye.